All right, welcome back everyone. This is a Calculus 2. So in this video, we are going to talk about 5.4 comparison test. So let me just give you a little bit of concept map, what we have done in chapter 5. So we talked about sequence and series. So actually we've been focusing on series. So this is all the summation of the, each term of the sequence. So we write it, let's say there's Sn. We've been proving that whether the given series is a divergence or convergence. Do you remember that? And then to define whether it is divergence or convergence series, we've been using a couple different testing. So if you remember, we talk about divergence testing and another methodology, integral test. And then third one, if you remember, p-series test. And then today, I'm going to introduce comparison test. So just go back to our previous video and lecture notes. We've been emphasizing on the characteristic of each divergence, integral, and p-series test. So by utilizing those tests, you can define whether the given series is a divergence or convergence, right? So keep going back to the previous learning and check it out if you forgot. So today we are focusing on comparison test, and also it helps us to find out the given series is a divergence or convergence. So let's take a look at the work, okay? So here is a comparison test. As you see from the name, something you need to compare with another thing. So here is the concept. Okay. So the definition is a little bit like complicated, but actually it is very simple. If you have, right, this is a summation node, and let's say I have something. So this is a general form of the sequence, and we are adding all the summation of that each term of the sequence. And then let's say we have a series, one series, and I'm trying to prove that whether it is a divergence or convergence. So what the comparison test saying that you are going to create something that is really, really, really related to the given form of the series, okay? Especially you're gonna look at this AN. So this is what we usually write it. This is a space where AN, right? So you're gonna find out the form that are really, 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 really close to AN, and then you are going to compare and then make the inequality relationship. So usually you're gonna say like an increasing relationship if there's something that is a similar AN, or you can say AN plus 1 or AN minus. I don't know. I'm just trying to give you guys example. I'm gonna compare this AN with another form, but that is really close to AN. So if you have that form, if it is a divergence, automatically this is a divergence, isn't it? If it is a convergence, automatically this is a convergence. So we're gonna compare those are two different function, and then check it out, the larger size or smaller, or you can have the other side, you can compare. You can find out another one depending on the function. So if you say this is convergence, automatically this is a convergence. Or you can think about the squeeze theorem as well. So comparison test, it's very useful because as long as you have some relationship between AN plus 1 or AN minus 1, you can say that this is going to be divergence or convergence without doing any complicated work. So let me just give you the example. So I think I need to make a space. So here is my example. I want to prove that, let's say I have n second power plus 1 in the denominator. Your job is find out whether this is divergence or convergence series. All you need to do, you need to look at this, right? So which one? How to compare this one to another one? So you're gonna create something that is really, really close to 1 over n to the second plus 1. So Usually, you're going to look at the first term of the denominator. So I'm going to compare this one, 1 over n to the second. Okay, I think there's a relationship, and then infinity, I'm going to compare these two. 1 over n second plus 1 and 1 over n second, that's not a big difference. They're pretty similar. And let me double check. So I do have 1 over n to the second plus 1, 1 over n to the second. When n is a 1, it is going to be 1 over 2. This is 1 over 1. When n is a 2, it is going to be 1 over 4 plus 1 is it's going to be 5. And then this is going to be 4. When n is a 3, this is going to be 1 over 10. This is 1 over 9. So hold up there. When you compare these two, what did I find out? The relationship 1 over n to the second is always larger. 1 is a larger than half. 1 over 4 is a larger fraction than 1 over 5th. 1 over 9 is a larger fraction of, than 1 over 10. So my relationship is a concrete now. So I can say this is always less than the other function. So we can set up this relationship because this is so true. So I don't know how to find out whether this is a convergence or divergence, but I know how to do this part because this is a much simpler fraction. So what are you guys going to do? You can do a bunch of different tests, divergent test, integral test, p-series test. I might be using the p-series test. Do you remember that? If the exponent is greater than 1, it's automatically convergent. So we prove that simply this is the convergent, therefore that is going to be also convergent. So this is the comparison theorem because here you cannot use a p-series test. P-series test, you have to get only n over p form, not the additional constant. So therefore, once you find out the similar one, prove it, whether this is a convergent or divergent, right? And then if it is convergent, yes, this is a convergent. If it is divergent, that's going to be divergent as well. So you need to find out something that is similar to the given an. That's what I'm talking about. Okay, so this is the comparison test. You can also utilize to find out whether it is a divergent or convergent test. Does it make sense? All right. So if you guys got this concept, can you show me your thumbs up? Does it make sense to you? So we're going to do a couple more examples like that. So I'm going to keep using comparison theorem. Does it make sense to you? So this is just one example. We're going to keep practicing and hope you guys have a better confidence. What do you guys think? Are you guys okay with that? Are you guys okay with that? I just want to make sure. If you got that one, I love to see you guys thumbs up. So it's getting better. Yep. So that's why we are introducing so many different type of tests. So let's take a look at 3 more. Here we go. All right. This is like, same type of question. I want to know whether this one is a convergence or divergence series. Again, this denominator looks complicated, right? So comparison test gonna help us. So you might be thinking, I told you the easiest way you can find out the comparison function, just to look at the first one, right? So you might want to compare VS, simply 1 over n to the third. And I'm gonna do literally compare this one and this one. So let's create a table one more time. So I have a 1 over n to the third plus 3n plus 1, a little bit heavier denominator, but this is n to the third. So let's just compare, right? So if n is a 1, this is a 1 over 1 plus 3 plus 5. And then this is 1 over 1. If n is a 2, 8 plus 6, 14, 15, and then this is going to be 8. So you're going to keep on going all the time. this is a larger. 1 is a larger than 1/5. 1/8 is a larger fraction than 1/15. So I found out that this fraction is a larger than this fraction all the time. So therefore, I can set it up. This relationship is going to be true as well. So what do you need to do? All you need to do prove that this is a convergence or divergence. Again, you can use the integral test, the divergent test, whatever it works for you. The easiest one, I can see that n to the p form, 1/n to the p form, you can use p series test. So absolutely p is greater than, in this time p is a 3 and greater than 1. It is going to be convergence on the right side. Therefore, this is also going to be convergence. That's how you're going to prove it. You need to make sure this relationship is always true. So compare, just write a partial term, and then you can just make sure that this is a true relationship. Then the right side is a convergent, left side is a convergent. Right side is divergent, left side is divergent. So you can prove that way. So same work, we'll keep on going. So let me minimize a little bit, okay? So likewise, we're gonna keep practicing a second example. I'm gonna change the color green. All right, so 1/2 to the n plus 1. Again, this denominator looks complicated. Ugh, are you really gonna adding? And it's a little bit difficult. So I'm gonna find out the similar one to 1/2 to n plus 1. The key point, you can compare. What do you think? 1/2 to the n only. So let's just create a table. So 1/2 to the n plus 1, 1/2 to the n. So plugging in n equal to 1, I'm just looking for the relationship. Which one is a larger and smaller? So if it is 1, 3, 2, 2, 2 to the 4 is a 2 to the second is a 4, 5, 2 to the is a 4. 8, 9, this is 8. So obviously, the right side is always larger. 1/2 is a 0.5. 1/3 is a 0.333. So definitely larger is always then bigger than the left side. So therefore, I can confirm this relationship is going to be always true as well. Are you guys following? So therefore, now you are going to check whether this is a divergence or convergence. Dun, 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 dun. Wait. In this time, P series is not going to work because we have a 2 to the n. And then if you look at this is a 1/2, 1/2 to the second, 1/2 to the third, 1/2 to the fourth. Definitely this is a geometric series, right? So they're keep multiplying 1/2, keep multiplying 1/2 for the next term. So how do I find out if you have a geometric series? The formula was A1/1 minus R, okay? If there's a specific number, it is a convergence. So A1 is the first term, 1/2, and then common ratio is also 1/2. So 1/2, 1 minus 1/2, so they're going to be 1. So what does it mean? The series, if you keep adding 1/2, 1/2 to the second, if you keep adding, they're heading to 1. So this is a convergence series. So we prove that this right side is a convergence. Therefore, this is also convergence. So in this time, I didn't use a P series test. I use a geometric series. So you should think about, different testing, right? Depending on the situation, you should use a different one. So that's why second one, we are using geometric series. So that was the formula, whether it is convergence or divergence. So that's number 2. So you see that we need to see a bunch of different testing. We never know which one you're going to use it. So chapter 5 is introducing different tools to see whether it is a convergence or divergence. So this is one, this is very mixed. So you should think about it. All right, so we are getting better. So I'm gonna do slowly think about it. Okay, so if you guys, so far so good, can you show me your thumbs up? Okay, so you got it. You got this. So now let's take a look at the third example. Ooh, what do you guys think? ln n. So you might be confusing. I might need a little bit of space for you. So let me change the color blue. So this one, I want to know something that I want to compare. Ooh. So ln is a little bit, complicated denominator. Obviously, you see that. So I might be comparing something, easy one. So this is ln. So this is 1 over ln n. Which one you want to think about it? So we need to test a couple ones. So how about 1 over n? Okay, so I'm just choosing simple one, and then I'm just testing it. If n is a 1, ln 1, which is a 1, this is 1. So at the first stage, they're actually equal. 1 over ln n is the same as 1. So it's going to be 1. But once n is increasing, ln 2, 1 over 2. Which one is a larger? So if you want, you're going to go to decimal. Just Google it. 1 over ln n, ln 2. What is that number? So you can evaluate it. ln 1 over ln 2, you can calculate it if you have a calculator, and then this is a 0.5. So I'm just going to the decimal. If you're going to decimal, 1 second quickly, because I want to know 1 over what is ln 2. So they say it's a 1.442. And then that is definitely greater than half, correct? And then n is a 3, 1 over ln 3. It's going to be larger than 1 over 3, but let me double check. Now it is going to be 3. So it's definitely greater than 0.1 over 3. 1 over 3 is a 0.666 something. So what I observe, this is going to be happening. The left side in this time is larger than the right side. Are you guys okay? That's okay. Sometimes it's going to be, different, direction. So now all you need to do, you're going to check whether limit, and actually that's why they begin from 2, because here they're same number. So we begin 2. I'm going to check whether this is divergence or convergence, right? So what I know, 1 over n, this is a so popular one. So this one, now you can use a p-series test, because there's invisible 1. P equal to 1, it's not greater than 1, so it is going to be convergence. Do you remember p-test? P-series test, p equal to 1. It is always divergence series. P is greater than 2, then it's convergence. 1 over n to the p. So therefore, this is going to be divergence. And then because of the relationship, we prove that this is going to be happening. This is also going to be the divergence. That's the complete answer. Okay. So once you prove this relationship, once you prove this relationship, that's your evidence. If this is divergence, that is divergence. If this is a convergence, that is a convergence. So you need to prove that relationship by checking with a couple partial terms of relationship. Okay, so I'm going to show you entire number 1 to 3. So that's the comparison test. Nothing is a special. So I gave you like a strong technique, which one you're going to compare. Usually the first term of the denominator, right? So that's going to be something you can compare easily. Okay, especially ln n, it's more complicated. So 1 over n, this is something you can choose. So this one is a little bit tricky, but you can think about it. Okay. All right. I'm gonna do a couple more because you want to practice more. So I'm gonna keep on going. So let's go to the next 3 example. Are you ready? If you're ready, can you show me your thumbs up? All right, so let's take a look at the next question. Here we go. Another 3 questions. Let me get rid of that. Ooh, we like this type of question already. You feel it, which one you want to compare. You feel like 3n to the 4, but you know, if you compare just n to the 4, that's a fine too. So I might be comparing the first term, 1 over n to the 4. And then let's create a table. And then 1 over 3n to the 4 plus 1 versus 1 over n to the 4. So when n equal to 1, I'm trying to define the relationship. It's going to be 1 over 4, 1 over 1. So obviously it's going to be larger, but you can check double. Just check, you know, a couple more. 3 to the, you know, if the denominator is getting larger and larger, the entire fraction is getting smaller, smaller. That's a rule. So if I have 2, 16 times 3, 36 plus 1 is 37. So 1 over 37 versus 1 over 16. So obviously the right side is larger when I check with the couple partial terms. So therefore, here is this one. So you know what? This one, you can think about it. Now, how are you going to check? This is obviously, you can see P series test, you want to use it because of 4. P equal to 4 greater than 2. Absolutely. This is a convergence. So therefore, the left side is also convergence. That's how you check. Okay, because we proved that this relationship is always true. All right, so likewise, let's take a look at the second one. The 3 to the n. Ooh, okay, so first term. So we're going to compare with n equal to 1, 1 over 3 to the n. So again, you can check the relationship. What is that? 1 over 3 to the n plus 1, 1 over 3 to the n. So n is a 1. What happened? 3 plus 1 is a 5. This is a 3. When n equal to 3, 9, 12, 13, 1 over 9. Obviously, larger hand is a greater than all the time. And then, do you think we can use a P series here? Nope. P series only n to the P, 1 over n to the P. But we have a constant 3. So you're going to write 1 over 3 to the n, 1 over 3 to the second. This is, you're keep multiplying 1 over 3 to find out the next term. This is geometric series. So to know A1 over 1 minus R, the first term, 1 over 3. Common ratio is also 1 over 3. So 1 over 3 over 2 over 3. So we have 1 over 2. So what does it mean? This convergence, this is series, is a convergence. They're heading to, if you keep adding, the next term, they are getting close to 1 over 2. Therefore, convergence. Therefore, the left side is also convergence. Boom, 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 boom. We got it. Sorry, let me go up. So I'm just trying to show you a similar question. So you see when you're going to use a P-series test, when you're going to use a geometric or integral test, convergent, divergent test, check it out. All right, one more. So let me change the color. Again, ln. So one thing, if you have 1 over ln n, the convergent, the comparison, you compared 1 over n, right? If you have a 1 over ln n plus 1, just look at this part. So you're going to compare 1 over n plus 1. That means if you have a 1 over ln n plus 2, you're going to compare 1 over n plus 2. Because this is from the, if you take the integral, you're going to go back to n plus 1 over n plus 1, n plus 2. So that's where the relationship coming from. But just be aware, this is a little bit of technique. If I have 1 over ln n plus 4, you're going to compare with 1 over n plus 4. So just keep in mind that rule. So we have this one, which is we're going to compare 1 over n plus 1. So we have 1 over ln n plus 1. You're going to compare with infinity 1 over n plus 1. So I need to compare the size, which one is larger. So plugging in when n equal to 1, when n equal to 2, da 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 da. So if you go to decimal, tell me what is ln 1, ln 2. So this is 2. So here they're actually same, right? Oh, actually not the same. What is a 1 over ln 2? I can calculate it. Yeah, it's a 1.1444. This is a larger. 1 over ln 3, 1 over 3 larger. So in this time, we have left side is a larger. Okay. So it usually, right, if you have the left side is larger, the answer should be divergence. If the right side is larger, usually the answer should be convergence. But you just need to double check, because we know that this one, you need to prove whether this is a divergence or convergence again. So here, watch me, what are you guys gonna do? 1 over n plus 1 still looks complicated. So again, here, I'm gonna make a star. We have a second comparison test between infinity, n over 1, 1 over n plus 1, versus, what do you guys think? Infinity, n plus 1, 1 over n. So you see that? We are trying to prove this relationship. But first, to find out whether this is a divergence or a convergence, you need to define what that is first. This one's still complicated. So I have a second comparison test. I'm going to compare this one, 1 over n plus 1 and 1 over n, right? So you're going to prove this. You're going to prove this. Now, if it is divergence, this is a divergence. If it is a convergence, this is a convergence. So what I found out here, finally, I can use the p-series test. So which is n equal to p equal to 1 is invisible 1. So this is going to be divergence. So this is a divergence. Therefore, this is a divergence. Therefore, this is going to be divergence. So I told you if your left side is larger, usually the answer is a divergence. So therefore, the last question, I had a second comparison pass because this middle one is still complicated. So you need to compare with another one, 1 over n. So we already know this is a divergence, therefore divergence. Therefore, the answer that we are looking for is also divergence. Does it make sense? So think about it. For the rest of the question, you're going to find out the same answer by using the second test. Okay? It's going to be still, everything is going to be divergence anyway. So that's how we are, practicing on how to use a comparison test. That's it. And I'm going to do one more concept before we're going to, finish, 5.3. So are you okay with that? Okay. All right, if you got that one, I love to see you guys invisible thumbs up. I'm pretty sure if you're watching this video, you can pause and you got this, right? So just think about those logical thinking, right? So another concept that is related to comparison test, I'm gonna show you, sometimes we can utilize a limit concept because, anyway, they are getting larger and larger. If you have a limit, obviously you can define whether they have a convergence or not. So let's take a look at that concept. So this is actually, we are not using a lot, but I just want to share, with you because textbook has that information. So one thing, is, if you love the general way of using comparison tests, like I show you the example, go for it, okay? But sometimes we have a super complicated, fraction. Then I suggest to use the limit comparison test method. So what that means is, so you might have some fraction for your, general form of the sequence, and then limit help us to see directly whether they have a limit or not, right? So if you can, calculate the limit, that means they're heading to some number. That means you can convince other people, hey, there is a convergent series or a divergent series. So what I'm saying is, from the limit concept, if you have a limit, actually that is equal to 0, right? If you prove that an over bn, so this each an bn, it's a sequence. Okay. If you prove that each an bn is divided by each other, and then they exactly equal to 0, that implies that the series of bn and series of an, both of them should be convergence. That's a theory. In other words, when you divide it by an over bn and evaluate the limit and they go to infinity, that implies that each series of bn and an, they're going to be both divergence. Okay, so I will show you. So we have 3 cases. Limit, let's say an over bn, whether it's not equal to 0, where it is a 0, whether it is a 0 or infinity. If this one equal to 0, that means both an, bn series are converges, okay? If infinity, both an, bn series are diverges, okay? So we're gonna convince that idea. So let me just show you quick example. So let me show you just quick example. So you feel like, oh, what is going on? So hold up there. I'm gonna show you that example according to that theory. So let's say I have a series form, summation n equal to 1, infinity an, and I have n equal to 1, infinity bn. Okay, so let's say we have a and bn. So I don't know whether this is a divergence or convergence, okay? So we don't know. And then I have a specific example. Let's say I have 1 over 2 to the n minus 1. So what I'm saying here, this fraction indicate that, right? The numerator is going to be an. The denominator, we're going to consider this as bn. Are you okay with that? Because according to the limit, so what I'm saying is, let's say we have this example, okay? And the numerator is an, denominator is a bn. So that means I want to prove so I have a little bit, 1 second. So let me just double check limit comparison theorem. So let me double check. So we have 1 over 2 n minus 1. And then let's say we have an over bn. So what I'm saying is, let me double check. I have a little bit of typo. I'm going to here, okay, because here, let me just go back to the question. So I want to know this is a divergence or convergence, right? So we can use 2 different tests. One is comparison test, okay? Second one is limit comparison test, sorry. So this is actually what I want to compare. So let me just explain one more time. Let's say, so ignore this one for now, it's not really important. But anyway, This is a true question. This is a real question that I'm looking for. Let's say I have a 1 over 2 to the n minus 1 series. I want to know whether this is a divergence or convergence. So automatically, you might be thinking comparison test. So you are going to compare this one versus 1 over 2 to the n, right? Because you're going to use the first term. And I know, if you compare this two, the right side is always larger. And then you automatically feel this is a geometric series, right? We just practiced 1 over 2 to the n, 1 over 2 to the second, 2 to the third, da 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 da. They keep multiplying 1 over 2. So a1 over 1 minus r, we do have 1 over 2 divided by 1 over 2, they're going to 1. So we know that because of this relationship, this is a convergence. So this is going to be convergence. So if you are using comparison test, we prove that this is a convergence. I'm using another method, limit comparison test. So this one, I'm going to do it. I'm going to show you how to do it. Find out two forms. So this is one thing we have. 1 over 2n minus 1. And then, yes, you're going to compare with same thing, 1 over 2 to the n. So what I'm saying is this one is going to be your an. This is going to be your bn. Am I clear? Okay. You're going to find out you have those two. And then we know that their relationship is clear. Larger, right side is always larger. So now what I'm going to do, according to the limit, we can use the limit an over bn. I'm checking whether it is equal to 0 or not equal to 0 or infinity. So limit n infinity, an is 1 over 2n minus 1 over bn, 1 over 2 to the n. I know, looks ugly. But if you simplify this fraction, oopsie. Let me a little bit smaller. If you make it a little bit simplified, this double fraction means 1, 1 cancel. It means 2 to the n minus 1. Actually, 2n over 2n minus 1. Just so you're going to divide it and then, clean, cancel everything. So this fraction becomes that. And now I'm trying to evaluate the limit. So top in the numerator and denominator, you have both 2 to the n. So to find out the limit, I'm going to divide it by 2 to the n everywhere because this is the highest degree. So the limit, 2 to the n divided by 2 to the n, 2 to the n divided by 2 to the n, 1 divided by 2 to the n. So limit, we have, this is going to be 1 minus 1 over 2 to the n. And then now you're going to have infinity, 1 over 1 minus infinity. 1 over 1 minus 0 is a 1 over 1, 1. So you have the same answer. Limit comparison test indicate that this function, that series we are looking for, is also converges heading to 1. So this is the converges. We just proved that. So what I'm showing you, I'm just showing you two different comparison tests. One is a very traditional one without limit. Second is a more modernized way, because sometimes it's hard to find out the one that you are going to compare all the time. So in that case, you're going to choose some number. You can change it simply n to n plus 1. Then you're going to use the limit and evaluate it where they're heading to. So this two method is under comparison theorem. One is a more traditional, another one is a more likely modernized way for the complicated fraction. So anyway, I just wanted to share with you, both of them are indicating this series is a converges anyway. So that's a limit comparison theorem. So as I mentioned, so that means that, okay, we just proved that this is not equal to 1. That means that it is a convergence. So that's why this is convergence and that is a convergence both. Okay. So that's a limit comparison theorem. Okay. So I'm going to hold up here. So we're going to just practicing just 2 more. Nothing is special. And I'm going to just do 2 more limit comparison theorem, if you guys okay. So let's take a look at one more example. Can I go to the bottom? Are you guys okay? So it's going to be fine because I'm going to do more practice with you guys. So can you show me your invisible thumbs up? Everybody okay? So let's do the following couple more. So actually we just did this example. So it's going to be above there. So I'm going to do the second question. There we go. So in this example, we're going to use a limit comparison test to determine whether the given series converges or diverges. So what did I say? You need to find out something that you want to compare. If you can, that's going to be the first term each, because they top and bottom numerator, denominator, they have the same highest degree n. So it is going to be, you know, this is going to be happen. So what I'm saying is, you know that you can compare the size, and then here it's a little bit complicated. It's not going to be work for the P series, maybe the geometric series, but I'm not going to use the classic one. We're going to use the limit comparison theorem. So therefore, we're going to use limit comparison test. So we say that this part is going to be an, this is going to be bn, correct? So the limit comparison test said an over bn. So I'm going to plugging in an 2 to the n plus 1 over 3 to the n entire divided by 2 to the n over 3 to the n. So if I simplify, the bottom 3n cancel. So the limit and approach to infinity, it's going to be 2 to the n plus 1 over 2n remaining. And then now I'm just evaluating what the limit of that function. So you're going to divide it by everywhere, 2 to the n. So 1 second, we're going to simplify. We're going to do limit and approach to infinity. So we do have 2 to the n. So 2 to the n plus means 2 to the n times 2, correct? So 2 to the n divided by 2n, 2 divided by 2n, because I'm divided by 2n everywhere. So therefore, it's a 1, 1. So limit, we have 1. This is a 1 times a 2 over. We have a 2n remaining, because everything is a 1. And then 2 over 2n remaining. And now you're going to plugging in the infinity. So let me just double check. 2 over 2 to the infinity. If it is getting larger and larger, 2 over, it's a larger, it is going to be 0. Are you following? So do you remember 1 over 0, whatever number of 0 in the limit, it's close to 0. So therefore, they're heading to 0. It is converges, right? So therefore, we found out it is a convergence. So you can prove that this is a convergence. This is also convergence. If you don't like the limit comparison test, that's okay. You can just use the general comparison theorem test, right? So we know that this is the geometric because of 2 over 3 over n, 2 over 3 over 2. You can find out a over 1 minus l, that they're going to be heading to the sum number anyway. So it's a convergence as well. But what I'm showing you in this question, we are using the limit comparison test using limit. So we proved that it's going to be 0, which is a convergence. So therefore, the answer is also convergence. Doesn't matter, even though you're using comparison or limit comparison test, they're going to give you the same answer. Just I'm showing you another version of comparison test. Okay. All right. One last question for today. The last question. All right. So I'm going to make a space. So this one, I'm gonna change the color. How about the, I don't know, I'm gonna change something like this dark green a little bit. I don't know, this one, good. Okay, let's do this one. So I'm trying to know whether this is divergence or convergence. So you could use, many different ways to prove whether this is a comparison or whether this is a convergence or divergence. Let's take a look at the example. Which one you want to use? So here, I might be using two different cases. So case one, let's just do the simple one. Limit comparison. So let's think about it. What are you guys gonna do? We have to compare. You might be thinking 1 over n, right? So let's just think about it. 1 over n to the 1 over n to the second. Which one you want to compare? 1 over n to the second? Yeah, let's do the 1 over n to the second. Yeah, so I can compare with that. So I'm using the limit comparison test. So what are you guys going to do in this case? This is going to be an, am I right? And this is going to be bn. So therefore, limit an over bn. So limit ln n over n to the second over 1 over n to the second. So this is a cancel. That means we have ln n over 1. That means just ln n. So now you're going to plugging in the infinity. It's ln infinity. This is infinity. So this is the divergence. What do you guys think? Hold up there. Let me double check with case 2. Just the traditional comparison theorem. So let me see. We already know we're going to compare these two. So let me copy this, copy and paste. So we know already the comparison one. So if it is, so we are doing this work. So let me see this one. We can use a P series. So P is a 2 in this time, correct? And then is greater than equal to 2. Is this say it's a convergence? So what I'm saying is, in this example, when you are using comparison test, they say the answer is a convergence. But when I'm using the limit comparison test, they say it is a divergence. So you have something in trouble. They have a contradiction now. I told you the both limit and comparison test should give you the same answer. But what I'm looking at this two different case 1 and 2, when I'm using two different tests, the limit comparison and comparison, they're talking about different answer. One is a divergence. So what I'm saying is, that's how you know this 1 over n to the second is not a good choice to use. So you have to, it is ln n over n to the second. You thought that 1 over n to the second is a great one to compare, but as you see that, it turns out it has not the same answer. So this comparison is not a good choice. You have to choose another one. So that's why we're going to choose another one. So sometimes you have to be careful when you choose the one that you are going to compare with. Check both answer. If they're contradict answer, that means you are comparing, how do I say, comparing one that you're, compare between two. That's not the good one. Okay. So which one you want to talk about it? Maybe we have to think about another one. So I'm going to go back to, so we're going to go back to here. I'm not going to compare with this one. No. Okay. So another way you can do, you're going to choose some different exponent instead of 2. What if you have n over 3 over 2? Right? So I'm just choosing another one instead of using 2. You could choose a 3, you could choose a 4, but you're going to have to keep, finding the contradiction. So I'm just choosing, another one, 3 over 2. Okay, I'm going to compare this one. So we're going to use both comparison limit, comparison test, and then you have to do comparison test. They have to give you the same answer. So first one, now this is an, this is a bn. So limit an ln n divided by n to the second divided by 1 over n to the 3 over 2, right? So it looks a little bit complicated, but if you simplify and approach to infinity, I'm going to simplify as much as I can. If you simplify, it is going to be ln n and ln 1 over 2. Oh, actually, ln n over n to the 1 over. You're going to calculate it. Okay, please calculate that. So now you're going to use the infinity. So if you're plugging in, this is infinity over infinity. It's on the determinate form, so we have to use L'Hopital's rule. So take the integral both of sides, top and bottom. So we're gonna take the limit in ln n prime and 1 over 2 prime. So if you do, it is going to be ln n is going to be 1 over n. If you take the integral, this is going to be 1 over 2 and negative 1 over 2. Sorry, it's a little bit ugly, but I'm just showing you. So anyway, this is going to be limit 1 over n, 1 over 2, 1 over radical n. So now you could use, sorry, again, indeterminate form, infinity over infinity. So just take a one more time derivative top and bottom. So ln 2 radical n prime over n prime. Okay, I just simplify this one, this fraction. So anyway, you will get limit 1 over radical n. I already calculated, that's why I already know what's happening. So what I'm saying is, you're gonna keep simplifying. This one become that, this one, you're gonna take the derivative, become this, and then you're gonna take the derivative of that, that's gonna be this one, and then now you can do 1 over infinity, this is a 0. So it actually looks like convergence. So we have to check with the comparison test. If it is a 0, then that's your answer. So we do have the regular comparison test. It's a simple, right? Because it's a P, according to the P series, we already know, and is it 3 over 2, which is a greater than, is it greater than 2? Is it greater than 1? Anyway, it's greater than 1. So I just want to clarify one more time. The P series, maybe I wrote something wrong. It's a greater than 1 anyway. It's a convergence, right? Like a P equal to 2, 3, 4, or 1.5, whatever, greater than 1. So if I just go up, I think I say greater than 2, that's my wrong. It's greater than 1 anyway, convergence. So because of that reason, so same thing. If it is greater than 1, my bad, anyway. So we can count 1.1, 1.2, whatever. So this is 1.5, automatically convergence. So both limit comparison test and comparison test indicate that this question is going to be convergence, especially heading to 0. So this question, the reason why I'm showing you, sometimes we made a mistake to choose the right the one that you're going to compare. So therefore, just check it out, both the tests, if it gives you the same answer. If not, you have to choose another one, okay? So that's all about the limit comparison test. And I will skip this one. You can try those 2 questions. I think you could use either, comparison test or limit comparison test. So in this question, definitely you feel like you want to compare with that. Here, you want to compare with the 4 to the n. So check it out. What are you going to get? So far, we talk about divergence test, integral test, p-series test, geometric series, comparison test, the limit comparison test so far. And then you're going to utilize one of them to find out whether the given series convergence or divergence. Okay. So that's a 5.4. I think you guys are good to go. Check it out. The video that I embedded in each quiz, that's also going to be helpful. Okay. So before you guys close this video, can you show me your invisible thumbs up? Are you guys okay with that? Does it make sense? 5.4, we talked about comparison theorem, comparison test to see whether it is a convergence or divergence series. Okay, I will stop recording at this moment. So when you come back into the next video, I'm gonna move on 5.5, and then you guys can finish 5.4 quizzes. And if you have any question, help each other through the discussion board.